Hi boys and girls, this is lecture 7.5. The topic, separation of variables and the logistic equation. Consider a differential equation that can be written in the form m of x plus n of y dy dx equals 0, where m is a continuous function of x alone and n is a continuous function of y alone. In these cases, all x terms can be collected with dx and all y terms with dy, and a solution obtained by integration. Such equations are said to be separable, and the solution procedure is called separation of variables. We've seen this technique before, but here we're going to apply it to more complex differential equations. Let's look at a couple of examples. Here we have x squared plus 3y dy dx equals 0. Rewritten with variables separated, 3y dy equals negative x squared dx. Notice the x squared was subtracted over, and then dx was multiplied to the right side of the equation. In this equation, we have sine x y prime equals cosine x. Rewritten with variables separated, dy equals cotangent x dx. Dividing by sine gives us cosine over sine, which is cotangent, and then y prime, when written as dy over dx, gives a dx that can be multiplied to the right side of the equation, resulting in dy equals cotangent x dx. In this example, we have xy prime over e to the y plus 1 equals 2. Rewritten with variables separated, 1 over e to the y plus 1 dy equals 2 over x dx. In this example, x was divided to the other side of the equation, and then y prime written as dy over dx gives us a dx to be multiplied to the other side of the equation, resulting in this rewritten version. Let's practice our separation of variables technique. We're going to find the general solution of x squared plus 4 dy dx equals xy. We're going to want all of our x variables on the right side of the equation with the dx differential, and we're going to want all of our y variables on the left side of the equation with our dy differential. So let's get started. We have x squared plus 4 dy dx equals xy. First, I'll multiply both sides of the equation by dx so that that differential will be on the right side of the equation. Now let's divide both sides by x squared plus 4. This gives me dy on the left side is equal to y times x over x squared plus 4 dx. And now dividing both sides by y gives me dy over y is equal to x over x squared plus 4 quantity dx. Now that our variables are separated, we can integrate both sides of the equation. On the left side, I'm going to have natural log of y, and on the right side, this is also a natural log scenario, but I do need to manipulate the integrand a bit. If u is equal to x squared plus 4, du is 2x. I need to insert that coefficient and multiply on the outside by the reciprocal 1/2. This means that my integral will be 1/2 natural log of x squared plus 4 plus c sub 1. Notice I didn't have to put absolute value bars around this argument, since this quantity will always be positive. Now let's use a property of logarithms and bring this coefficient around to become the exponent of this argument. Natural log of y is equal to natural log of x squared plus 4 to the 1/2 power plus c sub 1. Then we can exponentiate both sides of the equation. This gives me y equals e to the natural log of x squared plus 4 to the 1/2 plus c sub 1, which means I can rewrite this as e to the natural log of x squared plus 4 to the 1/2 times e to the c sub 1. This means now the e and natural log cancel, giving me y equals, this becomes a coefficient, e to the c sub 1, then I have the quantity x squared plus 4 to the 1/2 power. But since e to the c sub 1 is simply another constant, my final version will be y equals c and then x squared plus 4 to the 1/2 power. And that's your general solution. Given the initial condition y of 0 equals 1, find the particular solution of the equation xy dx plus e to the negative x squared times the quantity y squared minus 1 dy equals 0. First, we're going to move this xy dx term to the other side of the equation. That means on the left side, I'll have e to the negative x squared times the quantity y squared minus 1 dy is equal to negative xy dx. Let's rewrite this, putting this quantity with the negative exponent in the denominator, y squared minus 1 dy over e to the x squared is equal to negative xy dx. Now you can see that we're going to multiply the e to the x squared to the right side of the equation. At the same time, let's divide by the y. So this results in y squared minus 1 dy over y is equal to negative x e to the x squared dx. Now the variables are separated and we can integrate both sides. On the left side, since the denominator is a monomial, we should simplify this further and write this as the integral of y minus 1 over y dy equals the integral of negative x e to the x squared dx. On the left side, I'll have 1/2 y squared minus natural log of y. On the right side, if my u is x squared, my du is 2x, which means I need to place 1/2 on the outside of the integral. Furthermore, my du is positive, so I'll change this to a positive 2x and remove the negative to outside the integral with the 1/2. This means my integral will be negative 1/2 e to the x squared plus c. Now I am solving for a particular solution, and I do have an initial condition to help me do this, the ordered pair 0, 1. Replacing y with 1 and x with 0 will allow me to solve for the particular c. 1/2 times 1 squared minus natural log of 1 is equal to negative 1/2 e to the 0 squared plus c. This gives me 1/2 minus 0 equals negative 1/2 plus c. c, therefore, is 1. My final equation, 1/2 y squared minus natural log of y is equal to negative 1/2 e to the x squared plus 1. Now, in an equation like this, I'm not going to be able to solve for y, but I can do a few things at the end to make it a bit cleaner. Multiplying everything in the equation by 2, for example. This will give me y squared minus 2 natural log of y equals negative e to the x squared plus 2. And we'll let that be the final version of our equation. Find the equation of the curve that passes through the point 1, 3 and has a slope of y over x squared at any point xy. That means our differential equation dy dx is equal to y over x squared. Let's separate the variables and rewrite this, resulting in dy over y is equal to dx over x squared. I'm going to rewrite this again, dy over y, and the right side will be x to the negative 2 dx. Now that the variables are separated, we'll be able to integrate both sides of the equation. This will result in natural log of y is equal to negative 1 over x plus c sub 1. Let's exponentiate both sides of the equation to solve for y. Y is equal to e to the negative 1 over x plus c sub 1. But the right side of the equation can be rewritten as e to the negative 1 over x times e to the c sub 1. And of course, this can now become the coefficient of the exponential term. Y equals c e to the negative 1 over x. We're going to solve for a specific c, however, using our initial condition, which is 1, 3. Therefore, when y is equal to 3, we'll have c e to the negative 1 over 1 3 equals C over E, which means that C is equal to 3E. Therefore, my particular solution will be y equals 3E times e to the negative 1 over x. The rate of change of the number of coyotes, n of t, and a population is directly proportional to 650 minus n of t, where t is the time in years. This means we'll have an exponential growth model. When t equals 0, the population is 300. So we have this initial condition. When t is 2, the population has increased to 500. And then we're going to find the population when t is equal to 3. So let's set up our differential equation. dn dt, the rate at which the population is changing, is proportional to 650 minus n. Let's separate our variables and rewrite this differential equation. We'll have dn over 650 minus n is equal to k dt. Now that the variables are separated, we can integrate both sides of the equation. Since our u here is 650 minus n, we need this to be a negative du and a negative on the outside of the integral. This becomes negative natural log of 650 minus n is equal to kt plus c sub 1. Let's divide both sides by that negative. Natural log of 650 minus n is equal to negative kt minus c sub 1, and now exponentiate both sides of the equation. This results in 650 minus n is equal to e to the negative kt times e to the negative c sub 1, which we know is just another constant. Solving for n here, we'll have n is equal to 650 minus c e to the negative kt. Now let's use our initial conditions to solve for the specific c. We'll start with 0, 300. 300 is equal to 650 minus c times e to the 0 power. This means 300 is equal to 650 minus c, which means that 350 is equal to c. This makes our equation n equals 650 minus 350 e to the negative kt. Now it's time to use our second initial condition. 500 is equal to 650 minus 350 e to the negative k times 2. Subtract 650, that gives me negative 150 equals negative 350 e to the negative 2k. Dividing by negative 350 gives me 3/7 is equal to e to the negative 2k. And then when we take the natural log of both sides of the equation, we get natural log of 3/7 is equal to negative 2k. This means that k is equal to 0.4236. So our particular solution will be n equals 650 minus 350 e to the negative 0.4236t. Now let's use this particular solution to find the population when t is equal to 3. n equals 650 minus 350 e to the negative 0.4236 times 3 yields a population of about 552 coyotes. Our final topic in today's lecture is the logistical differential equation. As we have seen, the exponential model is derived from the fact that the rate of change of a variable is proportional to the value of y. The differential equation dy dt equals ky has the general solution y equals c e to the kt. Exponential growth is unlimited, but when describing a population, there often exists some upper limit L past which growth cannot occur. This upper limit is called the carrying capacity, which is the maximum population, y of t, that can be sustained or supported as time t increases. A model that is often used for this type of growth is the logistic differential equation. dy dt equals ky times the quantity 1 minus y over L, where k and L are positive constants. A population that satisfies this equation does not grow without bound, but approaches the carrying capacity L as t increases. From the equation, you can see that if y is between 0 and the carrying capacity L, then dy dt is greater than 0 and the population increases. Y between 0 and L makes this fraction less than 1, which makes this quantity positive, resulting in a population increase. However, if y is greater than L, then dy dt is less than 0 and the population decreases. As you can see, if y was greater than L, this fraction would be greater than 1, making this quantity negative, resulting in a population decrease. The graph of the function is called the logistic curve. You can see that it approaches a horizontal asymptote, which is the carrying capacity of the population. And the general solution for the logistical differential equation is y equals L, the carrying capacity, over 1 plus b e to the negative kt. Integrating this differential equation produces this general solution. However, the techniques necessary for showing that integration process do not fall within the purview of this class. Instead, we'll simply use this general solution to obtain values regarding various populations. In this last example, we're going to solve a logistic differential equation. A state game commission releases 40 elk into a game refuge. After 5 years, the elk population is 104. The commissioner believes that the environment can support no more than 4,000 elk. The growth rate of the elk population, P, is dp dt equals kp times the quantity 1 minus p over 4,000, where the domain of the elk population, P, is between 40 and 4,000, and where t is the number in years. First, we're going to write a model for the elk population in terms of t. Remember, this is a general solution for a logistic differential equation. L is the carrying capacity. Our carrying capacity is 4,000. Therefore, our particular solution will look like this. Y equals 4,000 over 1 plus b e to the negative kt. We'll need to solve for b and k using initial conditions, and those come from the original problem. At time 0, there were 40 elk released into the game refuge. After 5 years, the population was 104. Let's use this first initial condition to solve for b. 40 is equal to 4,000 over 1 plus b e to the negative k times 0. 40 equals 4,000 over 1 plus b. When we cross multiply, 40 plus 40b is equal to 4,000, which means 40b is equal to 3960, giving us b equals 99. So our solution, y equals 4,000 over 1 plus 99 e to the negative kt. Now we'll have to use our second initial condition to solve for k. In order to solve for k, I'm going to use the second initial condition, 5, 104. This will give me 104 equals 4,000 over 1 plus 99 e to the negative k times 5. Cross multiplying will result in 104 times the quantity 1 plus 99 e to the negative 5k equals 4,000. Let's divide both sides by 104. 1 plus 99 e to the negative 5k is approximately 38.462. When we subtract 1 from both sides, we'll have 99 e to the negative 5k is equal to 37.462. And dividing both sides by 99 gives us e to the negative 5k is equal to 0.378. Let's take the natural log of both sides. We end up with negative 5k is equal to negative 0.973, and when we divide both sides by negative 5, we have k is equal to 0.195. Thus, our particular solution will be y equals 4,000 over 1 plus 99 e to the negative 0.195 t. Now let's use this particular solution to answer the next question. Letter B asks us to estimate the elk population after 15 years. Y equals 4,000 over 1 plus 99 e to the negative 0.195 times 15. After 15 years, there will be approximately 626 elk. Letter C asks us to find the limit of our function as t, time, approaches infinity. Notice in the function as we let t go to infinity, since this exponent is negative, we end up with e over infinity, which is a zero quantity. This means as t gets very large, our denominator gets very close to 1. Therefore, as t gets very large, then our population will approach 4,000 over 1, which is 4,000 elk. And remember, that is our carrying capacity. That's it for today's lecture. Great are the works of the Lord, studied by all who delight in them. Psalm 111:2. I pray that as you study, you find yourself delighted by his works. God bless you, boys and girls.